Python scope bugs can look random when you're still learning the language? In this video, we will go through 13 real mistakes with variables, globals, non-local closures, and functions. For every bug, you will see the broken code, why it fails, and the clean, fixed version. First, let us look at the scope mistakes that happen inside ordinary functions. These are beginner-friendly, but they break real scripts all the time. Imagine a small script with a module-level counter. We want a helper function to print the current value and then update it, so let us write the direct version and run it right away. Let us break down the error. The assignment makes counter local to the function, even on the earlier print line, so the function is not reading the global counter, it is trying to read a local counter before that local value exists. Now we fix it by making the data flow explicit. The function receives the current value as an argument, computes the next value, returns it, and then we store the returned value at the call site. Now we run the fixed version and the output matches the intent. The better habit here is to pass values into functions and return new values back out. Use this when a helper function needs to transform state because it makes the code easier to test and easier to reason about. For a quick practice variation, start the counter at 0 and call the fixed function twice. Before running it, predict whether the final counter should be 1 or 2. Here's a command line style script with a global mode. The function looks like it switches the app to production, but let us run it and check what the global value actually is. This is called shadowing. The function creates its own local mode, and that local name hides the global name while the function runs. Once the function ends, that local value is gone and the global mode is still development. Now we make the change explicit. The function returns the selected mode, and the caller decides to store it in the global variable. When we run this version, the final mode is production. The best practice is to avoid reusing important outer names for unrelated local values. When a function computes a new setting, return it with a clear local name, then assign it where the program state is managed. As a small practice step, rename the local variable to selected mode. The important part is that the global mode changes only where the returned value is assigned. Next, we will look at global state. The global keyword can make an error disappear, but it can also make a program harder to maintain. Suppose an analytics script tracks total views. The helper function tries to add a new batch of views, so we write the obvious version and run it. Python stops before it can print the updated total. A quick technical fix is to declare total views as global. Now the function really updates the module level variable, and when we run it, the total becomes 125. Let us pause on why this is risky. The function now changes program state that is not visible in its parameter list. That makes call order matter more, and it makes the function harder to test in isolation. Now we write the cleaner version. The function receives the current total, returns the new total, and the caller stores it. Running this gives the same correct number without hidden mutation. The best practice is to reserve global for rare module-level state that really must be shared. For normal calculations, return the computed value so the function stays predictable. For practice, add another update of 50 views after the first call. Keep the return value style and confirm that the final total is 175. Now we move to a Python-specific surprise. Blocks like if statements and for loops do not create a new local scope. Imagine a checkout script that gives members a discount. We only assign discount inside the member branch. Then we run the code with a non-member customer. The print line fails because no discount value was ever created. Python if blocks do not create a separate block scope, but that is not the issue here. The issue is simpler. If the condition is false, the assignment line is skipped. Later code cannot use a name that was never assigned. Now we fix it by giving discount a default value before the condition. Then the if branch can override it when needed. Running both cases shows a safe 0 for non-members and 20 for members. The best practice is to initialize variables before conditional branches when later code depends on them. Use the branch to update the value, not to decide whether the name exists at all. For practice, add a premium member case, keep the default discount at 0, use 20 for normal members, and use 35 only for premium members. Here's a report generator with an existing item value. The loop also uses item for each order, so let us run it and look at the final report line. The program runs, but the final value is wrong. Python for loops do not create a new scope. The loop variable lives in the current function or module scope. After the loop ends, item still exists and contains the last element from the list. Now we fix it by using a more specific loop variable name. The loop processes each order item, and the original item variable remains available for the report. Running the fixed version prints the correct report item. The best practice is to name loop variables for what they actually represent. Use names like order item, row, user, or file path, and avoid reusing names that will be needed after the loop. For a quick variation, rename the list to invoice lines and use line as the loop variable. Keep a separate report title variable and confirm it is unchanged after the loop. Now we move into comprehension scope. This is where Python 3 protects loop variables inside comprehensions, which is usually good, but it can surprise you if you expect those names to exist afterward. In real code, this often appears when a developer builds a transformed list and then wants to log the last item processed. Let's write the comprehension, then try to print user after it. Now we run it and see that the list was created, but the name user does not exist here. Let's break down why this happens. In Python 3, the loop variable inside a list comprehension is local to that comprehension. The outside code gets the finished list, but it does not get the temporary name used to build it. Now we fix it by making the outside value explicit. The comprehension still builds the handles, and selected user clearly stores the value we want after that. Now we run it, and the output is predictable. The best practice here is to treat comprehension internals as private temporary names. If you need a value later, assign it with a normal variable so the next reader can see your intent immediately. Next, we look at closure mistakes. These bugs are tricky because the code often looks correct, but the function reads the variable later than you think. Imagine a tool that builds one callback for each file type. We create the callbacks in a loop, and each callback looks like it should remember its own type. Now we run it, and every callback processes XML. Let's break down the result. The lambda does not store the current text value when it is created. It stores a reference to the variable file type, and when the callbacks run later, that variable already contains the final loop value. Now we fix it by binding the current loop value as a default argument. That default is evaluated when the lambda is created, so each callback gets its own file type. Now we run it and each output is different. The best practice is to bind loop values deliberately when creating closures. Use a default argument for small callbacks or a factory function when the callback has more logic. A retry helper often needs a small counter that lives inside a factory function. Here, the inner function tries to increment attempts each time it runs. Now we run it and Python raises UnboundLocalError before the first count is printed. Let's break down why this fails. The plus equals operation both reads and assigns attempts. Because there is an assignment inside the nested function, Python treats attempts as local there unless we say otherwise. Now we fix it with nonlocal attempts. This tells Python that the inner function should update the attempts variable from the enclosing function. Now we run it and the counter increases each time. The best practice is to use nonlocal only when the nested function is truly responsible for changing outer state. If the state gets more complex, use a small class or return a new value instead. This bug shows up in nested helpers that update settings or workflow state. The developer wants to change the outer status but uses global inside the nested function. Now we run it and see two different statuses. Let's break down the scope lookup. The word global skips the enclosing function and targets the module level name. That is why the outer status remains draft while a separate module status becomes published. Now we fix the helper by using nonlocal. This points status to the nearest enclosing function variable, which is the workflow state we actually wanted to update. Now the outer status changes correct. The best practice is to choose the keyword based on where the variable lives. Use global only for module level names, and use nonlocal for names owned by an enclosing function. Finally, we look at a function definition scope mistake. Default arguments are created when the function is defined, not every time the function is called. A validation helper often collects errors and returns the list. This version looks convenient because errors defaults to an empty list. Now we run it, and the second call unexpectedly changes what the first result contains. Let's break down why both outputs contain both errors. The empty list is created once. When Python defines the function, every call that does not pass errors reuses that same list object. Now we fix it with none as the default. Inside the function, we create a new list only when the caller did not provide one. Now we run it and each independent call returns only its own error. The best practice is to avoid mutable default values like lists, dictionaries, and sets. Use none as the signal, then build the mutable object inside the function when you need a fresh one. Now we are moving into class scope mistakes. These bugs are tricky because class bodies, instance attributes, and method locals look close together on screen, but Python resolves them very differently. This comes up in configuration-style classes, where a developer puts a value in the class body and expects every method to see it directly. Here timeout is defined on the class, but inside the method we use timeout without self. Now we run the script and Python cannot find that name in the method scope. Let's break down why this happens. The class body creates a class attribute, not a local variable inside each method. A method must reach object and class data through normal attribute lookup, so a bare name like timeout is the wrong lookup path here. Now we fix it by using self.timeout. That tells Python to look on the instance first, and then on the class if the instance does not override it. Now we run the script again, and the configured timeout is printed. The best practice is to be explicit about the kind of state you're using. Use self for instance behavior, and use the class name when you want to make shared class state obvious. That keeps the lookup path clear for both Python and the next developer reading the code. For a quick variation, try assigning client towhow equals 10 before calling connect, then create a second API client and compare the two outputs. You will see how instance attributes can override class attributes for one object only. In real apps, each user session should keep its own history. Here we put events in the class body, then append through Alice's session. Now we run it and Bob unexpectedly sees Alice's login event too. Let's unpack the wrong result. The list is created once when the class is defined, not once per object. When Alice appends to it, she mutates the same list that Bob reads through his instant. Now we fix the session by creating the list inside init. That gives every new user session its own events list. When we run the script again, Alice has her login event and Bob stays empty. The best practice here is simple. Mutable data that belongs to one object should be initialized on that object. Use the class body for shared constants or shared behavior, not for per-user lists, dictionaries, or sets. This prevents quiet data leaks between instances. For practice, add a second event through Bob after the fix. Print both sessions again and confirm that each object keeps only its own events. This is the fastest way to test whether your state is truly per instance. The final scope trap is about dynamic code execution. It is powerful, but it often makes name lookup harder to reason about and harder to maintain. In data import code, it can be tempting to create variables from incoming column names. Here, exec creates a name called total, and the next line tries to print it like a normal local variable. Now we run the script, and the function cannot safely access that generated name. Let's look at the real problem. Python functions do not become easier to reason about when variable names are created from strings at runtime. Even when exec writes into a namespace, normal local variable access is not a clean contract to build on. Now we fix the design by using a dictionary. The key can still be dynamic, but the storage location is explicit and predictable. When we run it, the value is read from the total key without scope surprises. The best practice is to keep dynamic names as data, not as variables. Use dictionaries when keys come from files, APIs, or user input. Your code stays searchable, testable, and much easier to debug. For a small practice step, add another key named tax and print the sum of total and tax. This gives you the same flexibility people try to get from exec, but with normal Python data structures. Now you know the most common Python scope mistakes and how to fix them before they break your code. If this helped, like the video, subscribe to Dev Level Up, and write in the comments which Python topic or bug pattern you want to see next.